Hi, my name is Autumn Swing. This is my Lab 2 Motion of a Falling Object for Physics 1. So to start with, the purpose of this lab was to observe and measure the position of an object as it falls from rest from a height. This was done in basically 5 steps, where first we recorded an object that is thrown and moves like a projectile through the air, in which case we used a paper ball as our system. We then took that video and imported in a tracker to gather the object's motional data, which is just its initial and final position in the time. We then took that data and imported it into FlowScript in 2 ways. We did one with only gravity acting on it, and then another one where it was gravity and drag. And the goal of doing all that was to compare the models to see how they aligned, in which, for my data, they were very similar. So some key concepts. First is Newton's second law, aka the momentum principle. This law states that force on an object equals the rate of change of its momentum with respect to time. This gives us the formula F net equals delta P over delta T. This formula can be rearranged to give us the position update as shown on the left with RF equals RI plus V average delta T. And it also gives us the velocity update formula, which is shown on the right with VF equals VI plus F net divided by mass times delta T. The other 2 key concepts that we need to know is the gravitational force near Earth's surface and the drag force. These are crucial to this data, as that is what is needed to know to be able to do the glow script models. So the gravitational force near Earth's surface is given to be a value of negative 9.8 meters per second squared. This is applied as F net when no other variables act on an object, and it is given in the vector 0, negative, mg0. Drag force, on the other hand, is a resistance force in which it acts against an object in motion. So, for example, the air molecules or the particles in the air create a force of their own, which acts as drag on a moving object as they are pushing against it. In this experiment, the drag force was upwards. For our trackable analysis, we used a paper ball that was just like a piece of paper that was scrunched up into a paper ball, and everything else acted as the surroundings while that was our system. The observation start time is at 0.0333 seconds. This is because the ball needed to be fully in the air in order for the test to be run properly, and this occurred at this time because this is when it fully left my lab partner's hand. And using tracker, we were able to find the ball's initial position, which was 0.0850, 0.10560, and the final position was 1.6088, 0.02900. The time of observation was also roughly 7 seconds. And then that data and the models are shown on the right. So I did take this data and put it into GlowScript. This is the first one where we are just doing gravity. So the F net is just the gravity force, which is just 0, negative mg0, which can be calculated as shown in the data on the underneath all the text in the second red box, where Fg, which is the force of gravity, equals the vector 0, comma, negative ball mass times 9.8, and the ball mass is defined under system mass as 0.2 grams, which we weighed it after we record the video. And the velocity update and position update were used to gather this part of the lab as well. So I took the Newton's second law and took the rearranged version of it and used the ball velocity and ball position to calculate how it moved. And then I calculated this part of the data, and then the net force was calculated only using Fg. However, with drag, it was pretty much the same model as before. However, we had to use Fd. Fd is calculated by doing b times the absolute value of the vector v squared. This forces F net to be equal to Fg and Fd, as shown on the right in the red box, where the net force is F net, where F net is Fg plus Fd. Everything else is basically the same. And then on the left, it shows where I calculated the drag force, in which my drag force value was 0.003, and it shows how I calculated that with the v hat equals norm ball velocity, and then force of drag equals negative b times ball velocity squared times v hat. So these are all my models for the data. On the left is my tracker, in the middle is my glow script with no drag, and on the right is my glow script with drag. While looking at these, they look almost identical, if not identical. My tracker data is a little bit like its start value is lower because I used the data after it fully left the guy's hand for the other two. However, if you look at where it is roughly, they all very similarly line up, which means that the drag was not super significant in my data. As with the drag, it makes almost no difference on the one with no drag. And so they're all very similar. So for my discussion, do any of the models predict a terminal velocity? I do not think that any of my models predict terminal velocity. This is because for both the models done on GlowScript, the velocity versus time graphs are both linear. They both have a straight linear slope, and they don't even dip. But to find terminal velocity, you have to find the sum of the drag force and buoyancy, but there isn't one in my data, or if there is, it is very hard to calculate. And so I do not think that in this experiment I reached terminal velocity. I also think this may be because the ball was not falling for long enough. I think it only fell for maybe 2 seconds, and I don't think it had enough time to really reach terminal velocity. And for my what ifs, if would the time this object takes to reach the ground be longer, shorter, or the same if it was thrown straight up with the same initial speed? If this occurred, the ball would reach terminal velocity sooner than if it was just thrown at rest. This is because when you throw the ball straight up, it has more time to fall, which gives it more time to reach terminal velocity and maintain it. So the longer that it is in terminal velocity, the easier it is to find or figure out where it entered terminal velocity and how long it was in there, which is not something I'm able to do because my object only fell for so long. So possible errors for this lab are that there's slight differences in the placing of the center of the mass of the ball in tracker. This is because in tracker I only got 20-ish frames of data, and it's a white object against a mostly white background, and so it's a little hard to see it. It's also moving very quickly, and it's really hard to track where exactly the center of the ball is, and this would impact the position tracker by a bit. We also are not accounting for any motion in any other directions. We did it basically mostly only on the y-axis and on the x-axis, but the x-axis is not as official. We mostly focus on the y-axis, so the x-axis may be a little off. There also may be rounding errors, because Tracker cannot spit out all of the values for what the data are. It gives me like roughly 4 decimal places, so that may be slightly off, as well as there may be inaccuracy when determining the drag coefficient, because it was mostly just like a guess and check and try to get the drag coefficient to be as similar to the gravity one as possible. And so that could be some possible errors. And that is all of my lab. Thank you.